All right, so here we go. So today we're continuing our quest of acid and base, Regents level, and we're just going over some homework problems. And remember one we're going to skip, but we'll talk about it. In this course, we don't do much of equilibrium constants, but I will tell you that equilibrium constants depend upon temperature. So the Kw value that we learned, which was 10 to the negative 14, which you learn is the product of the H plus or the H3O plus concentration. Put brackets to show it's the concentration times the hydroxide, gives us 10 to the negative 14. So temperature, that constant is temperature dependent. You don't need to know that, but it's there for your viewing pleasures if you think you do. Okay, now here comes the real questions, okay? 2. Equal volumes of KOH and HNO3. At this point, you should be able to recognize that what kind of compound is KOH? Well, you could say from previous units, it's a salt. It's ionic. K plus and the hydroxide ions stick together. This specific type of salt, though, produces hydroxides. And if you forget, we do have a table, my friends, in chemistry that helps us identify these compounds. And table L is our friend here, although I see that's not what I'm showing. So common bases, all right, have that hydroxide ending because they have the ability to change the hydroxide concentration in water. So that's a base. That has to be clear. It's a salt, but it's a specific type of salt that has a hydroxide ion that can be liberated in solution. What does that do to my pH if I increase my hydroxide concentration more than my H pluses or H3O pluses? pH goes up because the number that we talked about yesterday and Monday, this right here, if the hydroxide is going up, this number gets smaller. So it was 1 times 10 negative 7. Then it becomes 1 times 10 to the negative 8, negative 9. The pH is about this guy. Okay, so if I've got equal volumes of a base, what is this HNO3? There's an H in front. It's screaming to you that H's come off. And what are those compounds where those H pluses come off? They're acids. And HNO3 is listed there for your viewing displeasure under table K as an acid. So I've got equal amounts of acid and bases. What's the pH of the resulting solution? 7, because I have equal amounts of H pluses and OH minuses and H pluses from the acid. They make a pH of 7, which is neutral, which you should know. Protons, H pluses, equal hydroxides. Number 3, a hydrochloric acid solution differs from an NaOH solution. At this point, it's like saying an acid solution differs from a basic solution in that the acid solution, it's listed, okay, has what? Well, the acid solution has more H3O pluses. H3O pluses are synonymous with protons. So that doesn't make sense. So we cross number 1 off, maybe. Okay, so that doesn't make any sense. Turns litmus blue. HCl. This acid differs from a base, and the acid turns litmus blue. Well, I'm going to have to go to table table M. And when I go to table M, all right, I should see maybe that table M, what does litmus show me? Litmus shows me that at 4.5 and lower, it turns red. At 8.3 and higher, it turns blue. So if litmus is turning blue, I'm above 8.3. Is that basic or acidic? Basic, over 7. So acids can't be basic. That's why that makes no sense. Okay? So clearly, as we keep going here, party people, we see that will not conduct electricity. Well, think about that. Has a lower pH. 4 is the best answer. Acids have low pHs. They have a greater H+. What about this electricity thing here? Do acids conduct electricity? What do you need to conduct electricity? I brought Ernie back out here today. You need free ions. And do acids give off free ions? Do acids dissociate into free ions? If I had a hydrochloric acid, okay, what does it do? Does it break apart into H plus and Cl negative? And the answer is yes. Acids break apart into ions. Acids are electrolytes. What about bases? Do bases conduct electricity in solution? Does NaOH break apart into anything? What does NaOH break apart into? It's a salt. Is it going to break apart into Na plus and OH minus? Yeah, so acids and bases are also electrolytes. So C makes no sense, or 2 makes no sense because both an acid and base break apart into free ions, and Ernie's going to light up. Number 4, if the concentration of hydroxide, is that OH minus or H3O plus? I get confused. Where could I look? Table E lists your polyatomic ions. Hydroxide is OH minus. Is 1 times 10 negative 5. This solution is what? So if my hydroxide, here it is, OH minus concentration equals 1 times 10 to the negative 5. What's the pH? Is it 5? Is it all about the base or is it all about the acid and pH? P means little p of the H. So what? This 5 plus what is 14? 9. So the H plus ion concentration must be 1 times 10 to the what? Negative 9. And therefore the pH is what? 9. And because it's above 7, it's basic. Choice 4. Yes? Sure. So now its pH is 9, above 7, and we know it's basic. But look up here, party people. If I am a pH of 9, who's a bigger number? 10 to the negative 9 or 10 to the negative 5? Right, so there's more hydroxides when the pH is 9. That's why it's basic. All this comes together, maybe. Number 5. Which of the following is true of acid and base solutions of equal concentrations? They will not have the same pH. Acids have low pHs, bases have high. They have the same Kw. Yeah, Kw is that 1 times 10 to the negative 14. Okay? So that's the best answer. They do not both turn litmus red. The red color is only associated with anything less than 4.5 on this scale, which is acidic. And they both don't have the same amount of hydronium ions. Hydronium is H3O+. HCl has more of them. Number 6, what is the H3O plus concentration of a solution that has a hydroxide of 1 times 10 to the negative 3? Well, if the hydroxide's negative 3, the H plus or H3O plus must be 1 times 10 to the negative 11. 11 plus 3 gives me that 14, which is Kw. Which relationship is always exists in aqueous solution? It's basic. We just talked about that. The H plus is less than the hydroxide, choice 3. And number 9, which pH represents a solution with the lowest hydroxide? Lowest hydroxide means more basic and more acidic. And which has a pH that's going up or down is more acidic. Yeah, so pH of 1 is what you're looking at here. An indicator, table M, was used to test a water solution of pH of 12. Which indicator color be observed? Well, if you look at table M, phenolphthalein turns pink when it's 9 and above. So pH is above 9, so we'll get pink with phenolphthalein. Choice 4. Okay? All right, we'll skip 11. Okay. Everyone good? Any questions? Any Yes?
Can you explain number 8 again?
When a solution is basic, you're going to have a pH that's greater than 7. Here's an example. When the pH is 9, the H plus ion concentration is 1 times 10 to the negative 9. This means this must be 1 times 10 to the negative 5 because when these exponents add together, they give me the Kw, which is 1 times 10 to the negative 14. Okay? So, if I have a basic pH and this number is bigger, this number must be smaller. Therefore, basic pHs will always have more hydroxides. The pH is 9 because you're taking the positive value of the negative exponent, which is really a smaller number. So the pH rises, the single integer, but that's because this number gets smaller, and that's why bases or basic solutions have more hydroxides. Okay, it's a play on negative numbers. Okay, saying goodbye to that. Ooh, can't do that. Let's go to acid and base, guys. Let's take this out. This I gave you yesterday. The acid and base guys. I made this a couple years back when they had the juice guys on TV a lot. The juice guys with the nectar or something. I don't know if they're still in business. Well, they sold their juice company. All right. I think it was... what it was. Okay. So here we have to write some stuff down. Arrhenius acids, I should say. Let's make this bigger because I'm tall. And I can. Okay, Arrhenius acids. Number 1. Bottom line, to be an acid, this is the most simplest definition. Watch what I do here. Arrhenius is right here, AR. It's the most simplest in scope in definition for an acid. To be an Arrhenius acid, you simply increase or produce H pluses in solution. H pluses in solution are made from acids. That's it. The only thing positive in solution is this proton. Very simple. So if you look at table K, most of these are Arrhenius acids. Why? Because there's an H in front, telling you that H's slough off. Except for one. Look at CO2. CO2 doesn't have an H. Yet, it's an acid. So a CO2 doesn't have an H to produce in solution, so CO2 is not an Arrhenius acid, which led us to believe that this wasn't the best definition. But it's the earliest. It's the only one you really have to know in terms of name. So if you hear a name, Arrhenius something, a Grotsky acid, any name of somebody in front of acid, it's the simplest definition of an acid. And that means you produce H pluses, which is intuitive because acids are written with the H in front to show the H's come off. Now, Arrhenius bases are also very simplistic in their definition. Its small encompassing definition says to be an Arrhenius base, or a small definition, you produce OH minuses in solution directly from the chemical. So the only thing negative in solutions, is the hydroxide. So if you look at table L, or sometimes affectionately known as table OOL, okay, you'll see that I have, whoa, this chemical's got an OH to come off. Arrhenius base. Hey, KOH has got an OH to come off. Arrhenius base. Calcium hydroxide's got an OH to come off. Arrhenius base. Ammonia doesn't have an OH minus that comes off. It is not an Arrhenius base. But we know ammonia makes solutions basic. So you can clearly see that, although a nice definition, it doesn't fit all chemicals. So here ammonia is not an Arrhenius base. Now, what does ammonia do? Well, as I said yesterday, let's think about this for a second. Ammonia is basic, and I'll do this one more time. Here's ammonia. It's got a lone pair with water. What does it do? Well, that lone pair on the end can pull an H away from the water, an H plus. So this guy can accept the proton. So it's a base, and it's a better definition because it includes all of the Arrhenius acid definitions and those that don't fit. So in a Bronsted-Lowry base, to be a base, you are a proton acceptor, an H plus acceptor. Okay, now what happens? Well, if that's true, what is water acting like? If ammonia is the base, what's water doing by donating the proton? Acting as an acid. Bronsted-Lowry acids are proton donators, which is pretty what? Intuitive. Why is it intuitive? Because donators, I think I just misspelled that. They're proton donators. Why? Well, it's pretty, they donate their protons, keep it like that. Okay, they donate their protons because they have an ability to give that H plus to the base, or the base takes them. Don't really know, but the bottom line is there's a transfer of protons. The one that gives off the H plus, that's your acid. So Bronsted-Lowry acid and bases are more encompassing because they have the ability to not only accept their Arrhenius acid definition, but include, so their definition, the Bronsted-Lowry, Br, are able to accept all the Arrhenius acids and those that don't fit in the definition. So the Bronsted-Lowry acid and base definition accepts all of the others. Think with me for a second. Look at Arrhenius base. An Arrhenius base is basically a hydroxide ion. What does it do? Doesn't it accept an H plus from an acid? Of course it will make water. It's called neutralization. So yeah, it still works. So anything that's an Arrhenius acid is also. Okay? So Arrhenius acids. You produce H pluses in solution, the most simplest form of definition. Arrhenius base, you produce hydroxides. Okay? So to be one of these, you have to have a hydroxide or a proton. Bronsted-Lowry acids are better definitions because they are talking about donating protons to be an acid or accepting the protons to be the base. And they'll include the ones that are not there. Okay? So let's finish out this weak acid-base equilibrium problem. After the ammonia accepts a proton, what does it become? After it gets one more NH3, what does it become? Ammonium ion, right? It becomes NH4 plus. It gains a proton, so this becomes NH4 plus. And this becomes water, lost a proton, it becomes a hydroxide. So indirectly, by this Bronsted-Lowry base accepting a proton from water, it produces the hydroxides, which increase the pH, and that's how ammonia works. But we have to know this, party people, okay? And you don't have to know Bronsted-Lowry by name. You have to know it by, they use the word in this course, other definition of acid and base. Okay? So, if this was a base on this side, and it accepted a proton, now it's over here, and I should put a plus here because it gained a proton. Bad Grodzki, good pizza. Now, this is important. Focus. Focus. If I was a base on this side, how would I act going in the reverse? Let's make it an equilibrium like we talked about, double arrow. Well, if you don't know how to do this, this is the current condition. This is the future. In the future, this guy has what? One less H. How did it have one less H going this way? What must it have acted like to lose an H, to donate an H? Right, an acid. An acid, my friends, in chemistry. So this guy is an acid going in the reverse. And I know acids, according to the Bronsted-Lowry definition, or the other definition, donate H pluses. So this must have donated an H plus to the hydroxide. What's the hydroxide going forward? It's OH minus. Here it's H2O. How did it become H2O? What did it do going to the right? It accepted an H plus. So my friends in chemistry, accepting a proton is a base. And you are responsible for being able to, given this weak acid-base equilibrium, to figure out who your bases are and who your acids are. And I'm introducing a new word today called conjugate. The word conjugate means the same. This and this chemical are essentially the same, except plus or minus an H. These two chemicals are the same, plus or minus an H. We call these conjugate base or acid-base pairs. Okay? And they will ask you, who's acting like the acid? Why? Donating a proton. That's why this is acting as the acid in the forward. Who's acting as the acid in the reverse? This one, because it's donating an acid. Yes?
When we look at these questions, questions, are you gonna give us something to say, like what's acid and what's base?
Right. In fact, let's just go there. Okay? Let's just go there. So let's go to these questions. We started them yesterday. So let's go to this one. Okay, let's go backwards a little bit to go forwards. Okay, now I'm going to get rid of the stuff on top, and let's just do it. This I gave yesterday. Conjugate acid-base pairs. Conjugate means same chemical plus or minus. Sometimes they call this weak acid-base equilibrium. Okay, party people, here we go.
Do we have that?
Yes, you do. I gave it to you yesterday or Monday. Okay. So here's what you have to be able to do. You got to tell me who the acids are, who the bases are, and who the acid-base pairs. Now, here's how I do it. Very simple. Let's be crazy and go in order. Let's go in front. The one in front is acting as what? Well, let's see. HS becomes what? H2S. Now, in the future, we're starting here and it goes this way. So, current, future. In the future, it has one more H. How did that happen? It must have accepted. Now, throw yourself an arrow here. Boom, there's an arrow. There's H+. Now, what's the definition? If I accept a proton, what am I acting like? A base, right. And if the other one's donating a proton, it's acting as an easy peasy. Now, here's the rule. If it's an acid, if it's a base on one side, it's a what on the other? Acid. If it's an acid on this side, it's a hey. Now, if you don't trust me, watch. Go in the reverse. H2S becomes HS, going in the what? Reverse reaction. I have two H's, and in the future, I have one less. What must I have done to lose and donate one? I must have donated, I kind of gave it away, a proton, which must means I'm acting like a what? This one accepts one, hey, it acts as a base. So list the acids. You would say HSO4 negative, right? That's this one. And who else? H2S. Both of these are on the different side. You should be picking chemicals on different sides. Who are my bases? HS negative and SO4 negative 2. Those are my bases.
I have a question. Does the negatives, like, are those like important? Like, what if you leave them out? Is that?
They are important because that's the species. Yeah, you need to make sure you have them. Okay. Now, I'm not going to write this, but can you give me a conjugate acid-base pair? Can you give me the same chemical? It's an acid and base. Do you see the same chemical?
Yes.
Yeah, so I just erase all of this so it makes it clear. The conjugate acid-base pairs are here. Here is, make this pink, we have HS becoming H2S. And where's another one? HSO4. Those are my two conjugates. Same chemical, plus or minus an H. All right? Let's go on to the next one. When I erased that, kind of gave it away, didn't I? Okay. I want you guys to try this one. You didn't memorize what I just put. Who are the acid? Who's the base on both sides?
We did this one together.
Okay, we did it together, so I kind of gave it away. So obviously, if you don't know my friends in chemistry, I take the HNO2. It becomes NO2. It has what? One less N. So this must have donated an H+. So this is my acid. This is my base. If there's an acid on one side, it must be a what on the other? Base. And this must be a what? Acid. Who are my conjugate acid base pairs? Same chemical. And who is my other conjugate acid base pair? Right there. Okay? No biggie. All right? So that's what you have to be able to do. Okay. Now, one more point I wanted to make today. Okay? We talked about acid and bases. And if you go back to our acid and base guys, let's go to the acid and base guys. Let's go here. You notice there's CO2 listed in table K. All right? CO2 doesn't even have an H. So it can't even donate an H. So it's basically what it is, no pun intended, it is a Lewis acid. Not something that I'm going to talk about, but I want to show you something. I have, okay, two solutions. Okay? And let me put them somewhere first. Get this down. I'm literally myself. Now, these two solutions have two different chemical indicators in them. That's why they have a color. Now, before I even do that, watch this. Okay? Now, I have, what color is this in here? Green. We give off CO2. Now, CO2 in water will make an acidic solution. So right now it's green. And if you look on table M, bromothiamyl blue, if it's green, is what pH? In between the yellow and blue, like yesterday, correct? So if I've got a green solution right here, right? And I'm using bromothiamyl blue, that must mean that the indicator is in between its yellow and blue color, correct? Yesterday, if you had a pH of 7, bromothiamyl blue should be green. Okay, here's what I'm going to try to do. I'm going to try to blow into this solution. By blowing CO2, a respiratory gas, okay, that we give off as CO2. To show you that CO2 is acidic, hopefully if I blow enough CO2 in here, I'm full of hot air anyway, right? This should change color to what color? Where am I getting? If I'm adding CO2 to water, it's an acid. It becomes acidic. So turn yellow. So this should turn yellow. All right, we ready? I don't know. I'm ready. Okay, still green. Getting lightheaded. All right, is it light green? I'm almost there.
Ow.
It's changing, I think. Yeah?
Not really.
No. Okay, well, I'm going to keep trying. And while I do that, I have another demo here to show you, to prove you that, but I'm not proving there. Okay, now. Okay, let's put that, can we see it? Well, let's lower this so everyone can see what I'm talking about. Alright, put that right there. And, okay, so what I have here is two indicators. Okay, I've got bromothiamyl blue to the on the right, and something called universal indicator to the left, and I'll talk about that in a second. Now, let me just put this on the big screen. Okay. Hard to see, so put some more lights on. Okay. And let's focus on those chemicals.
Yeah.
All right, now, probably better look at it live. Okay, now, what I'm going to do is take some dry ice, which is what? We learned what this was, right?
I say, oh yeah.
Oh, now we got something good. Can you touch on it? Just focus? Are we good? Yeah. Woo! Okay, dry ice is CO2, right? It's CO2 in the solid phase. So my friends in chemistry, okay, we should know that dry ice is a brittle solid, isn't it? Why is it a brittle solid? It's made of, it's a molecular substance. So put a little piece in here,
It's frozen.
Oh, it's turning yellow.
okay? It's changing color. What does bromothymol do in the presence? Okay, what does bromothymol do in the presence of an acid? Turns yellow, doesn't it? Okay, let's put some over here. Now these indicators are changing color because the dry ice.
Wait, throw it over here.
Different day. Now this one is made up of phenolphthalein. And it's called universal indicator. It's got 3 different colors. This turns red in the presence of an acid. So as this goes, you should see a spectrum of colors. This one's going yellow because, actually no, it's getting yellow because it's getting acidic, because this is basically what? The one to the right is nothing more than bromothymol blue getting yellow, which we know about in the presence of an acid. And this is getting red because in universal indicator, it's a mixture of phenolphthalein, methyl red or orange, and bromothymol blue. So it's getting reddish color because of the methyl orange that's in it. Okay? And the green on the bottom represents the bromothymol blue. Okay. Talk about mad scientists right here. I'm trying to get to this color by just blowing in. I think I'm close.
Yeah.
Am I getting there?
Yeah.
Way too much.
Big difference.
I'm still a little green, but I'm getting there. Just trust me. I think it's almost there. If I fall over, someone catch me. Is it getting there? Yeah, it's there. It's almost there. It's almost there. Now it looks illegal. This is not changing because I put a buffer in here.
Do it.
All right. But I put too much. I'm going to stop now. All right. Well, it's getting there. Okay. All right. Last little demo. And we're running out. What's an electrolyte? What's an electrolyte? What does Ernie do in the presence of an electrolyte? Lights up. So, we know that pure water does not produce enough what? Ions to light up. So, metal to metal contact, Ernie lights up because it has free what? What do metals have? Free electrons. They hold on to them loosely. Now, something that's acidic, okay, should light up, but this is only slightly acidic. Okay, so what I'll do here, let's add a base. to this? What's going to happen to my color here?
It's gonna.
Go back to, so I'm adding a base, which should be increasing the number of ions here. So what should Ernie do? This is really. You get anything from Ernie?
No.
You have to increase the ions a lot for Ernie to light up. Okay? But if I take this beaker, whoa. Okay, made of pure water. Okay, Ernie doesn't light up. But if I was to add some acid, or in this case some base to it, what happens to Ernie? Okay, now why? Because Ernie, if you're a base, what do bases give off? What do bases give off? Bases give off hydroxides. Now if I have an acid solution, okay, an acid solution, if I was to pour this here, obviously I'm already in an acidic solution, this would go more red, this would go more yellow, but in an acidic solution, okay, in an acidic solution, if I can stuff these in here, what would Ernie do? Light up or not? Is an acid an electrolyte? Is an acid an electrolyte? Yes, of course it is. Why is an acid an electrolyte? Because it has free what? So here is an acid. Okay, so acids or bases both give off ions. So there's three things that make electrolytes now. Soluble salts, acids, and bases all break apart into ions. Okay?